Okay, everybody, we're going to get underway. As always, I appreciate you spending a little time with me. The plan tonight is we're going to finish up the ideas from chapter 9. And by ideas, it's within our very last topic, looking at molecular orbital theory. I'm going to have a couple opportunities to return to ideas that were earlier in chapter 8, chapter 9, sort of to begin to think back a little bit, somewhat as a review. But I really want to make sure we get a solid understanding for those ideas pertaining to molecular orbital theory. When the idea was first introduced, we saw that we were going to have both bonding and anti-bonding molecular orbitals with the designation sigma and pi. And last time we began to explore a little bit, well, what did we mean by anti-bonding? We were already somewhat familiar with the designation sigma and pi, but that was a new idea for us. And then in section 9.8, which we're going to practice this evening, we're going to look more at the energy level diagrams that we have when we move across the second period. And we want to be able to think about things and describe bonds in some ways that we've already been familiar with. We've already been looking at the idea of bond order, connecting that to properties like the bond enthalpy and bond length, but we're going to add a new one this evening, which is concerning the magnetic properties. So this topic, similar back to when we were looking at chapter 6 in our view of quantum mechanics, it's a very advanced idea, but that doesn't mean that it's too much for us to handle really in this class, because we have some very specific skills that we want to be able to do. One of the skills is, given a energy diagram with molecular orbitals, we want to be able to populate that with the correct number of electrons and interpret it. We want to be able to consider the resulting molecular orbitals and be able to apply notation and interpret notation like this, like sigma or sigma star. And then we want to bring both of those together, bring together the representations with where they would be on the map, on the energy diagram that shows where the different ones are found. Those are going to be our objectives. Those are what I'd expect exam questions to be. And I got a lot of polling questions this evening because I want to make sure that we can get a solid understanding of all three of those, so your time here is well spent. So first of all, let's look at that idea on the shape. So here I show the construction of a bonding molecular orbital and an anti-bonding. They're both given the designation sigma. Every time we bring together the atomic orbitals that have the correct energy, have the correct shape, every time that they overlap in molecular orbital theory, we're going to form both the bonding and the anti-bonding molecular orbitals at the same time. You don't have to say, well, which one of those form? They both are formed at the same time. A lot of good questions within perusal about, well, if they form due to the phases matching or not matching, how do we know that? Really good questions, but the answer is an easy one. We don't have to select one. Both of them are formed at the same time, both the bonding and the anti-bonding. Mathematically, what's taking place is something called, we're doing a linear combination of the functions that describe those atomic orbitals. We certainly don't have to do that mathematical part. Let's recognize, though, it's easy. In these diagrams, we always form both the bonding and the anti-bonding at the same time. Now, in terms of their designations, sigma means the same thing it did when we first introduced sigma and pi bonds with valence bond theory. Sigma has to do with the shape. Sigma means the electron density is along the internuclear axis. So in these pictures right here, the dots represent the two nuclei where the protons are. Internuclear axis is along that. As it's shown here, it's left to right. Sigma means you have electron density along that axis. The pi that we have here, excuse me, not the pi, the anti-bonding, this designation here with the asterisk, that means it's anti-bonding. An anti-bonding molecular orbital, all of those are going to have a node between the two nuclei, a vertical node, a node of some kind that bisects those two atoms. It bisects where the electron density would be if you were going to have a bond. The anti-bonding is removing electron density from the region that would be holding those atoms together to form a bond. So based simply on those two descriptions meaning, do we have electron density along the internuclear axes? And do we have a node present or not that is between the two of them? Let's just explore that shape a little bit. Let's explore how those are connected to our descriptions of different shapes. So let's say we have two nuclei here. And let's say I just made a shape, okay? I was just grabbing different things to have us explore. So let's say this shape somehow represents the electron density, where the electrons would be found. So I'm showing where the electron density is relative to the nuclei. I just want to practice a little bit these designations. So given that picture right there, given the shape of where the electron density is, would you call this sigma or not? And would you label it bonding or anti-bonding? Let me send you a poll on that. Is the shape of the electron density there sigma, or no, it's not sigma? Is it bonding, anti-bonding? I was typing these together shortly beforehand. My description is the shape sigma, no sigma. I'm not really proud of the my use of the English language there. And I want to practice a couple of these because I think once you get a better understanding of how the designation is put together, then I think you'll be able to match these up pretty well with our chemistry examples. So as far as first take right here, we're really split them as much as we possibly can be between whether this is sigma or not and bonding or anti-bonding. We're almost exactly half on both, half on both. So let me share my reasoning for this, and then we'll move on and try another one. So my reasoning on this one is, do I have electron density along the internuclear axes? It doesn't look like I have it along the internuclear axes. I have it off of the axes, either above and below. It's not along the internuclear axes. So I don't think it is designated sigma. How about bonding or anti-bonding? In order to be anti-bonding, I'd have to have, as it's drawn here, a vertical node separating the left and the right. I don't see that either. I think that this is not sigma. This would be an example of pi. This would be an example of pi that would be a bonding description. There is no vertical node separating the two, so I know it's bonding. And instead of being along the internuclear axis, it's off the axis. It's above and below. That would be my description for that. That would be my analysis of looking at the shape. Let's practice another one. How about this one? These are the two nuclei, okay? And I was just trying to make another shape of some kind. Would you call the resulting shape there sigma? And would you describe that as bonding or anti-bonding? I think I can send you the poll again. Same choices, okay? How about this one? Does this shape look like sigma? Yes or no? And would it be bonding or anti-bonding? Take about 10 more seconds. I had to get up and let my dog in. My door was shut and he was hanging out right outside there. So in terms of this one, sharing results, strong consensus that this would be described as sigma based on the shape. I agree. It looks like it's right along the internuclear axis. As far as bonding or anti-bonding, what I'm looking for is, do I have a region of electron density between the two nuclei? I was trying to say, yes, we do. Within this representation, I was trying to describe this as an example of a sigma one with electron density along the internuclear axis. And I don't see a node there. So I think that it would be described as bonding. Let me give you another shape. We have the two nuclei. I tried to make it so we have even more of a bizarre pattern within here. Let's say this was describing the electron density though. What would you describe with this one? How would you characterize this? I'm going to send same poll format to you again. Would this be sigma or is it not sigma? Is it bonding or anti-bonding?
Dr. Clark, can I
Yep,
ask a
yeah, go ahead.
question about the first one? So
Yep.
the like between the two nuclei, there isn't like you don't see electron density. So why was that one bonding?
Well, what do you think of the one that I have right here? Our third choice down. Is that bonding or anti-bonding?
I think that's anti-bonding.
I agree. And I think the key difference is within this third example right here, I would have like a vertical separation between the left and the right. In the one on the top right there, I don't have that vertical separation. I have electron density that would be found off of the internuclear axes, both above and below, but that could be used then to form a pi bond. That's the same sort of spatial arrangement where we had electron density when we looked at pi bonds before, when we were looking at valence bond theory. So the key thing that makes it anti-bonding would be if I have that separation, as they're shown here, between the left and the right. If I have these top ones, these could still be glue that would be holding it together. I could still have this be a bonding arrangement. I guess the key thing I'm looking for within that is, do I have this vertical separation or not? Does that make sense?
Yes, thank you.
Okay. So within this last one right here, the one that we just shared, strong consensus is anti-bonding. I agree. I see this vertical separation between the two. And if I have to say, is this sigma or not? I think it's an example of a sigma one. The electron density is present along the left and right, along that same axis right there. So this shows that you can have an example of something that would be sigma and anti-bonding. How about this one right here? I'm going to shoot it to you one more time. Does this look like sigma or not? And do you think, is it bonding or anti-bonding? And as the results here are coming in, I think we're getting a little bit better to recognize just sort of a little pattern recognition here. I think we're not there yet, meaning within several of these, we're at about 80% or so, 85% on our responses. But I want us to practice enough so that the folks, if you're here, I want us to be able to get this to 100% for this topic. I think we're getting better, but I think we're not quite at mastery yet for the group. Within this one, it looks like the strongest consensus is that it's anti-bonding and it's not a sigma. And I agree with both of those. In order to be bonding, well, I can't see that vertical node between the two. In order for it to be sigma, I have to have the electron density right on the left to right across along that internuclear axis. I can't be simply above and below it. So I'd say within this one, this would be back to an example of being a pi description, and it would be an anti-bonding one. So as I look at this, we've got all four examples here. We've got something that would be a pi arrangement that's bonding, a pi arrangement that's anti-bonding at the bottom, a sigma that's bonding, and a sigma that's anti-bonding. Let's look and see how these same patterns show up in the same designation as we start to see them with the molecular orbitals that are shown in the book. And here's an image of those. Okay, so I grabbed different ones that were within the e-text. The same kind of analysis based on their shape, we're going to do the same thing. That same designation, if it's sigma or pi, bonding, anti-bonding, let's give that a try. So I want you to look at these. There's 7 different images. which of these do you think are designating sigma arrangements? And in this one, select all that apply. Which of these do you think have electron density? If it's sigma, that means along the internuclear axis. I see a question within the chat as far as how might this show up on a test? What would be a representative question? This is a really representative question, right? You could easily have images given and you're asked to apply terminology like this. When I say one of our learning objectives is to be able to recognize the shape, make sense of them, it's trying to connect the symbolism that we have as far as whether something is sigma or pi with the same kind of figures. Take about 5 more seconds on this. So on this one, I see 3 strong results as far as being selected as sigma, 1, 3, and 5. With 1, yeah, I think I have electron density along where the internuclear axis would be, left to right. Number 3, same thing. And number 5, same thing. I think those are all really good examples. The only examples we have listed here of sigma. That makes all of the other ones, numbers 2, 4, 6, and 7, those are all examples of pi arrangements. There's electron density, but it's off of the internuclear axis. Now, next question, how about being bonding? Same kind of poll I'm going to shoot to you. Select all the ones that are bonding. On the description here, as far as whether something is bonding or anti-bonding, I like the suggestion that was earlier in the chat. If you're having trouble with bonding versus anti-bonding, you might be overthinking it. Something that is going to be anti-bonding, if you've got like this equivalent of this dashed line, if you've got a node in between the 2 nuclei, then that's going to be anti-bonding. Other than that, it's going to be a bonding molecular orbital. When I look within the analysis here for which ones are bonding, I'm seeing a strong consensus for 2, 3, and 7. I'm going to agree with all of those, okay? Because it sure looks like I have nodes that are present in 1, 5, 6, and 4. Vertical nodes that are present between the 2 nuclei. And that's not present in 2, 3, and 7. 2, 3, and 7 then are all bonding. Notice here within like number 7, there is a node. It is dividing the electron density as it's shown here between the top and the bottom, but it's not being this vertical one like we see with number 6 that is splitting between the 2 nuclei. The reason that number 6 is an anti-bonding, this node right here is saying you cannot have electron density in the region between the 2 atoms that you need in order for a bond to form. It's destroying a bond instead of building a bond. Same thing with number 5. You can have electron density, but you can't have it in the region where you need it to form a bond. Same thing with number 1. You can have electron density, but you can't have it in the region that forms a bond. That's what anti-bonding is designating. These are all ones that I grabbed out of the e-text, but they all come back to what the shape is, the designation of sigma or pi, and the interpretation for bonding or anti-bonding. help me out within these. You sort of have to visualize this one. So I'm curious, is there one within this group that you think is the most difficult to interpret, or the last choice is you can interpret all of them? Is there one of these particular shapes that you find confusing? Take about 10 more seconds for me. Yeah, I'm not surprised with this one, sharing the results. Number 2 wins as being the one that's the most difficult and the most challenging to visualize. I can get that because I know within the artist rendition here with their version, it's more difficult to see where they meant the 2 nuclei to be in the first place. It looks like they're trying to show the electron density in and out of the plane, one coming towards you and one going to the back. But I agree, without sort of having a better sense of what it was trying to designate where the nuclei would be, I agree that that would be the most difficult, I think, to visualize. Now, how do we begin now to use these to populate these? So this is something that we looked at before. This would be looking at what would it be to have an Li2 molecule, taking how we had on the far left and far right the electron configurations for each, and then in the center, the molecular orbitals that were being formed. As far as our designation, the lower in energy was the bonding molecular orbital. And above that, then we had the anti-bonding. And it looks like we had that being formed from the 1s. And then same thing being formed from the 2s. Bonding, anti-bonding, bonding, anti-bonding. If we're starting to connect what kinds of representations go with those for the molecular orbitals, this is the shape that goes with the bonding. This is the shape that goes with the sigma star anti-bonding. We practice how do we get to what type of bond it would be in terms of the bond order. We end up doing the number of the bonding minus the anti-bonding and cut that in half. So you could add up all of the bonding, and I see 1, 2, 3, 4, minus the 2 that are in the anti-bonding, 4 minus 2, cut that in half, it's a single bond. You could also, if you want, say, well, look, in this first group, the core ones, I have 2 in the bonding, 2 in the anti-bonding. There's not going to be any story there because they're going to, if you want to think about it, canceling out. I've got the same number in the bonding or the anti-bonding. So if you wanted to, you get the same answer if you started your analysis just right here. Said I've got 2 in the bonding, nothing in the anti-bonding, 2 minus 0, cut it in half, single bond. So my point is that when you're accounting for these, you could count all of them, or you could just count the valence one. You're going to end up with the same answer either way. Now, we also could look and say, well, what happens if we make this an ion? What if we make it a cation, like Li2 that has a +1 charge, or Li2 minus, Li2 that has a -1 charge, is an anion? My analysis there is I'm going to look at the molecular orbital diagram and recognize I'm either going to be removing an electron to make the cation or adding the electron to make the anion. I think in both of those cases, you get a bond order of 1/2. If you remove one of the electrons, or if you add an electron to the molecular orbitals, I think in both cases, you get a bond order of 1/2. I'm curious on that. Do you agree with me on that? Do you see what's going on? Do you realize, can you see how if you're making either the cation or the anion, you get a bond order of 1/2? We don't really have to worry about where did the electron come to or go to, meaning to make the cation, the anion. All we need to do is now put the correct number within the appropriate molecular orbital diagram. And with that, calculate whatever our new bond order is. Looks like, as far as the consensus on this, pretty confident that you can see where that's taking place. We're almost at 3/4 of the folks saying, yep, you see where that's coming from. Let me give you a little bit more detail on this one. If I am making the cation, I've got to remove an electron. I would be removing from the bonding right here. So now my calculation, I'd have a total of 3 in the bonding minus 2 in the anti-bonding, cut that in half. It would be a bond order of 1/2. What if instead I make the anion? I would be starting out with the original arrangement and I'd add an electron to the anti-bonding. Now my math would be I'd have a total of 4 in the bonding minus 3 in the anti-bonding, cut that in half. That's how I get a bond order of 1/2 in that case too. The strategy is the same. All I'm doing is figuring out how many electrons do I need to now place into the molecular orbitals. And now let me do my calculation of bonding minus anti-bonding and cut that in half in order to get the bond order. Now, when we're looking at this within our molecular orbital diagram, molecular orbital theory, it includes excited states. What do I mean by excited states? Well, I have this orbital that's vacant, that's above the ones that are being populated. We already saw this kind of thing take place when we were first looking at our models for the hydrogen atom. Whether we looked at the Bohr model or the Schrodinger model, we saw that a photon could come in, excite the electron and move it to an orbital that was higher in energy. And then when it came back down from that excited back down to the lower energy levels, photons were emitted, and that's what we were measuring on our spectrometer. So we had atomic orbitals for hydrogen that were not filled in the ground state. Those were present in the excited states, as excited states. And if the photon that came in interacted with the electron, it could move it up to one of those. Same thing takes place now. In molecular orbital theory, we've got these excited states. A photon could come in and it could remove an electron to a higher energy level. So in this case, if I had a photon come in, let's say the photon matched this energy transition right here. It could move it from the sigma 2s to the sigma star 2s. If it did that, what would happen to the bond? This was a question within Perusal, and people did a great job analyzing this. They said, okay, so if I move it up there, based on that new arrangement, my bond order is going to be 0. I would have the same number in bonding as in anti-bonding. If I have a bond order of 0, I don't think I have a bond anymore. I think what's happened is the photon has come in and it's broken the bond. I predict that's what happens if we have this promotion taking place. People did, I thought, a really good job describing this and thinking about this within Perusal. The idea here is that we can have bond orders of 1, bond orders of 2, we can have fractional ones. And as we connect these, as the bond order goes up, what am I thinking? I'm thinking if the bond order goes up, it becomes a stronger bond. The bond is getting shorter. It means a higher bond enthalpy. If I'm all the way down here at 0, I don't think I have a bond at all. So what I'm trying to review and connect a little bit here are different descriptions that we had for bonds. We talked about bond order, bond enthalpy, the relationship between the strength of the bond and the length of the bond. I mentioned within Perusal within here how I could connect this to an energy well diagram. This is what I mean by an energy well diagram. The x-axis on here is the distance between the two atoms, and the vertical axis is the potential energy. 0, that comes back to what we started, seems like the very first week of class, where we defined the potential energy of 0 being when the particles are far apart. And if they're attracted to each other, as they move closer together, the potential energy becomes negative, it gets smaller. So here's an energy well diagram in terms of the potential energy. Terms like bond order, bond enthalpy, they could all apply to this. They could apply if we're talking about molecular orbital theory, but energy well diagrams, they apply for any of our bonding models too. What I'm trying to do is take us back to when I think these were first introduced, probably in chapter 8, because this is an exam question topic all on its own. independent of molecular orbital theory, being able to interpret these diagrams. Very typical exam question. Notice if I have two different profiles here, I'm calling this line right here, the solid line, I think that's corresponding to a stronger bond. I'm seeing a greater bond enthalpy value. It's a deeper well. It's a shorter bond. All of those ideas are coming together if I compared the solid line with the dashed line. And when I say it's relevant for other bonding models too, let me ask you a question about that. So let's say we're comparing these two. Let's say that this blue arrow is pointing to the dashed line, and that corresponds to the nitrogen-nitrogen bond in this molecule, H2N2H2. What could the other one correspond to? The solid line that has the red arrow. So in order to answer this one, the reason I'm bringing this one up here, it sort of allows us to review and to think a little bit about where the ideas fit together. First of all, when I see these molecules being described right here, I'm not using molecular orbital theory for that. I'm staying away from molecular orbital theory on that, because we're only going to be doing molecular orbital theory for our simple second row diatomics. We'll see in a second that we could do it for N2, but I'm certainly not using it for these more complex molecules. But we can talk about the bonding in those. For those, I would start with the Lewis structures. This dashed line is said to represent the nitrogen-nitrogen bond in this molecule. Here's my Lewis structure for it. And I'm being asked to compare it to these other two. This would be a Lewis structure for N2. This would be a Lewis structure for the HNNH. All of these are Lewis structures that I think we should be able to draw. So take a second right here. If this dashed line that the blue arrow is showing, if that represents this first molecule, let me send you a poll. What do you think the solid line that the red arrow is pointing to would represent? In order to answer this one, I would be using the Lewis structures. That solid line with the red arrow corresponds to which one? Take about 10 more seconds for me. Okay, so within this one, before I share any results with this, let me talk it through, and I want to try to repoll. Okay, we're a little bit more mixed on this than I thought we might be. So first of all, let me talk through once again how I would analyze this, and I'm going to give you another chance. So first of all, I'm going to look just at this potential energy well diagram. I'm going to first draw my attention to the one that the blue arrow is pointing to, this dashed line. Okay, yep, it looks like there's a bond. It looks like it's moved lower in potential energy as the atoms came together. Got it. But now it's asking me to compare with the red arrow and that solid line. What do I see with the solid line? Well, for one, I see that it is a deeper well. I also see that it is shifted and it's at a smaller distance. It's more to the left-hand side here. So it looks like that solid line right here, the way I would interpret that, that looks like it is showing a stronger bond, a shorter bond, a bond with a greater bond enthalpy. So that's what I'm seeking to analyze right here. Which of these two molecules, both neither the N2 or the HNNH would you say have stronger bond, weaker bond compared to this first one right here? Let me resend the poll to you on that. My interpretation as those are coming in is that that blue arrow is pointing to what looks to be a single bond between the nitrogen atoms. That's the energy well diagram. That's the dashed line. It looks like then this N2, that's something that has a triple bond in it. It looks like something that is the HNNH that has a double bond in it. So in order to answer this one, I'm definitely thinking about the bond order. I'm definitely thinking about the bond order and saying, okay, what would be a shorter bond than the single bond? Well, a triple bond would be shorter. I think the double bond would be shorter as well. I think both of these are applicable. I think both of these could correspond to that solid line right there. Now, can you do this? Meaning, can you take a energy well diagram and begin to connect it to other things? I think you can. I think what you need to do within your analysis for this, I would really be focusing on the bond order. And from the bond order, I'd be trying to think about how stronger bonds have larger bond enthalpy, which means the well is deeper, the atoms are closer together. That's how I would be seeking to interpret this. Now, since I've brought up the idea of valence bond theory, you know, a lot of times once we have different bonding models here, students ask, well, which of these is best? Well, it sort of depends on what we're trying to predict or explain. Valence bond theory, I think it's really good at helping us determine the relative bond length and bond enthalpy that was found in molecules like this. If I were to use molecular orbital theory with this, it would be a really complex description. I think if I just wanted to describe whether it's a single bond, a triple bond, a double bond, and begin to explain that, valence bond theory would work fine. Now, when I say it would work fine, the Lewis structure is telling me if I've got a single bond, triple bond, or double bond. But remember, in valence bond theory, we then use that information to explain the bonding. We talked about how the bonds were being formed. Let me give you a review of that. So this first one right here, I think I have sigma bonds between the hydrogen and nitrogen, and sigma bonds between the nitrogen and the nitrogen. Those were single bonds. I think that the sigma bonds between the hydrogen and nitrogen, those were formed from overlapping the 1s atomic orbital on the hydrogen and the sp3 hybridized orbital on the nitrogen. How do I know it's sp3? I'm looking at the electron domain of that nitrogen, that inner nitrogen, and I see that it has 4 different regions, tetrahedral, so therefore it must be sp3 hybridized. The sigma bond that is being formed between those is being formed from the overlap of the sp3 hybridized orbitals that I have on each of the nitrogens. That's how I'm explaining the bonding in this molecule. If I'm using valence bond theory for N2, I don't really need to hybridize anything because I already have atomic orbitals that have the correct alignment. I could form a sigma bond between the nitrogens because I have an unhybridized p orbital that would be along that axis. So it already work. I can form the pi bonds because I have 2 sets of unhybridized 2p atomic orbitals that are perpendicular to that. One above and below, one front to back. So I don't really need to do any hybridization there to form a single bond, a double bond, and a triple bond. It works from there. So hybridization isn't really necessary within this one, but it's definitely necessary in this last one right here. Before I show my answer here of how I would construct and explain the bonding in this using valence bond theory. I want you to give it a try. I see bonds being formed between hydrogen and nitrogen, between nitrogen and nitrogen. I see a single bond, double bond. See if you can recall that information, then I'll share it with you. How does valence bond theory explain the bonding in that molecule?
Dr. Clark, how do you know for a linear molecule whether you need sp orbitals or not?
You will if it is a central atom that has something on both the left and the right. But if you don't have that, you need to be equivalent on both the left and the right. But if you have something that's just diatomic, anytime if it can just stick on directly, you've already got the correct orbitals that would align for it. If I'm looking at this one, I'm thinking, okay, I'm not going to hybridize anything with these hydrogen atoms. They have one s orbitals, they're going to be fine, but I do need to hybridize for the nitrogen atoms. I think that I can form sigma bonds between the hydrogen and the nitrogen.
Okay, because there's an asterisk where it wasn't central.
Pardon me?
Sorry, my internet cut out for a second.
Yeah, I know that, I'll put it this way. Anytime that you have ones that are going to be our central ones, I'm sure that those are going to be ones that we end up hybridizing. And I'm sure on your test, that's how it's going to be posed for you. Okay.
Okay.
Within this one, if I'm looking at my nitrogen atom, I see 3 different electron domains. So I know it needs to be sp2 hybridized. One of those hybrid orbitals can form a sigma bond with the hydrogen. One of those hybridized orbitals can form a sigma bond with the other nitrogen. And that leaves then the pi bond that gets formed. And that's from the overlap of our unhybridized p orbitals that remain on each of the different nitrogen atoms. So I know within here, this is probably the end of the line for valence bond theory, meaning our most advanced application. It's being able to think about how do we assign what's contributing to the different bonds. So this was sort of taking us back to that idea. And again, I know it's a pretty high-end idea, but it's a very typical exam question as well. Okay, doubling back here to molecular orbital theory. So with molecular orbital theory, we're again thinking how these p orbitals can overlap with each other. We're not hybridizing them. We're just looking at the resulting shapes that we have. If we bring together the p orbitals that are along the same axes, we see that we can have both a bonding and an anti-bonding. I think that we know the notation now here. It's sigma because it's along the internuclear axis in both cases. Sigma star for the anti-bonding because I have a vertical node in between. When I'm thinking about the other p orbitals, I have a set that would be above and below the nuclei and then also front to back. So each of those arrangements end up forming a bonding and an anti-bonding, a bonding and an anti-bonding. So I have more variety here when I'm looking at how p orbitals can overlap with each other. I see both bonding and anti-bonding that are sigma, bonding and anti-bonding that are pi. I've got 2 examples of those. And the 2 examples that are anti-bonding that are pi. So when I populate now my energy diagram for this, once I get to the p orbitals, a little bit more is going to be going on. So let's use this here to explore what we have for molecular orbital theory, how it explains the bonding in O2. So I've moved along, I'm moving left to right. I'm over now looking at a diatomic molecule near the right-hand side of the second row. So on the far left and far right in this diagram here, this would be the electron configuration for oxygen, the atom. 1s2, 2s2, 2p4. So first of all, when I look at my molecular orbital theory, I'm going to have an overlap between these s orbitals and make a sigma, sigma star. There's a total of 4 electrons that I'm going to put in there. 1, 2, 3, 4. When I think about how the 2s and the 2s overlap, they will again form a bonding and an anti-bonding. sigma, sigma star. The 2s is designating which ones they came from. I've got a total of 1, 2, 3, 4 electrons. So when I put those into the molecular orbitals, I get 1, 2, 3, 4. So these would be the description when I filled up the molecular orbitals coming from the 1s with the 1s and the 2s with the 2s. If I were to think at this point, well, what would the bond order be? I don't think any of these are really contributing to that story, because in both of these cases, I have the same number of bonding and anti-bonding. This is sort of back to that example where, well, you could look at the whole thing if you want, but it's these valence electrons of the two p's with each other. That's where the story is going to be that describes what the resulting energy level diagram is that we populate that leads to the bond order. So when we combine the 2p with the 2p, this is the arrangement that I then have for oxygen. Let's talk this through. I see a sigma. That must have been when the 2p orbitals were pointed directly at each other along the internuclear axis. I've got two that are degenerate at the same energy level that are bonding, that are designated pi. Okay, that's because I had two that were perpendicular, either above and below or front to back. They're both at the same energy level. And that's what I term degenerate. Above that, I see the pi star, anti-bonding. And above that, the final anti-bonding that would be the sigma star. So now the skill I want to practice right here is if I'm adding electrons within here, I have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons that are going to populate these. Let me show you how I put those in. I put in 1, 2, 3, 4, 5, 6, 7, 8. I'm putting them into the molecular orbitals the same way that I would have put them into atomic orbitals. I'm putting them in from the lowest energy and going up from there. I'm putting them into each box, which represents a molecular orbital. I'm putting them then in consistent with the Pauli exclusion principle. Each box can only hold 2 electrons, a spin up and a spin down. Notice if I double back how I put them into this region right here. I was following Hund's rule. I put them in unpaired and then I paired them up. And then I put my final 2 in because they're degenerate into their own orbitals and I put them unpaired. My point is that when I've populated these molecular orbitals, it's exactly the same approach, exactly the same strategy that I would have used for atomic orbitals. I'm going from the bottom up. I'm putting them in independently. I pair them up. And then I move on from there. I'm following the Pauli exclusion principle and Hund's rule. So I'm curious within here. Give me some feedback. Could you have done this for O2? Could you have done this, but you're not sure exactly how many electrons to use? Or you're still struggling to do this? Even if I told you how many electrons, you'd probably struggle with it. So if you're analyzing and you're working here for O2, where do you stand? 1, 2, or 3? Do you think you could do it? Do you think you can do it, but you're still a little bit struggling with the number of electrons? Or even if I told you the number of electrons, you still have issues with it? Take about 10 more seconds on that for me, please. Okay, so share results with folks. For the most part, it appears that the issue, if you do have an issue, it's about how many electrons that we end up using in this. And this is definitely in the category of, this is something that I learned a long time ago. And I know that students raise this point all the time, and it's really difficult for me to answer you because it seems so obvious to me. So I'm not saying that like, oh, I'm a pro with molecular orbital theory. I'm just saying it's difficult for me to get into your head on this one and understand the challenge that you're seeing to determine the number of electrons. I think partly it is once we start adding electrons to the center region, it sure seems like we've got a hell of a lot of electrons there. How many do we end up having? They were in atomic orbitals, now they're in molecular orbitals. What's going on? So this is the representation that you see where it shows both the electrons being found on the outside and on the inside. But conceptually, once we put the electrons into the molecular orbitals, if you just want to imagine the ones on the far left and the right vanishing away, that's fine. All we want to do is put into the center region the correct number of electrons that we have coming from those atoms. So I find it helpful looking back to say, let me take the time and see on the far left-hand side for oxygen, what was the electron configuration? 1s2, 2s2, 2p4. So on the far left, 1s2, 2s2, 2p, 1, 2, 3, 4. So this far left-hand side, that's an oxygen atom. The far right-hand side, 1s2, 2s2, 2p4. Okay, that's an oxygen atom. Now in the center region, I'm going to take that same number of electrons. It's as if they're just dumping it in from the left and right-hand side. All of those electrons now are going to be populating the molecular orbitals. We can do it in stages. In this bottom group, I have a total of 1, 2, 3, 4 electrons that are going to be placed into these molecular orbitals. That's the 1, 2, 3, 4. In the next group, I see a total of 1, 2, 3, 4 electrons that get placed in 1, 2, 3, 4. That leads me to the ones now with the p. I see a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons must go into here. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 electrons that were placed in. So I'm not like double counting anything. I'm just shifting them from atomic orbitals into the corresponding molecular orbitals. Let's work through a little bit more, but I know that that counting one, I'm not trying to dismiss your issues or trying to get settled on that. I know a lot of times that's the key sort of stumbling block. Now, these are the different shapes that correspond to the molecular orbitals that were formed here. Let's see if we can make sense of those, okay? These are the ones that you classified earlier for me as being bonding. There's bonding that goes with the sigma. There's 2 bonding that go with the pi. These are the ones that all have these vertical nodes in them, so these are the antibonded. We have 2 examples that are degenerate. Those were the pi ones, and way at the top, that would be the sigma one that would be antibonded. So the thing that we practiced a little bit earlier, now we're seeing where those match up in terms of the molecular orbital diagram. When I look at this molecular orbital diagram, when I'm looking at these ones that are formed with p orbitals, I see 2 that are degenerate that have the same energy and 1 that is different. Same thing with the antibonded, 2 that have the same energy and 1 that is different. It comes back to the orientation. I could have them along the same axis. There's 1 set of p orbitals that can combine like that. And I have 2 sets that were off the axis. That's why I have this situation of 1 and then 2 being degenerate. 1 and then 2 being degenerate. Now, if I put this all together, I get a bond order of 2 for O2. We could add and analyze all these bottom ones, but let's just use the valence electrons here, the 2p. In the bonding, I see 1, 2, 3, 4, 5, 6, minus 2 in the anti-bonding. 6 minus 2, cut that in half. Yep, bond order of 2. But with O2, something interesting happened in order to get this. Notice what happened right here. And this is the way I sort of envision what happens, okay? As we're thinking about the electrons here, it's as if I added electrons to form a single bond. I added more to form a double, then a triple. And then as I start to add the anti-bonding, what I envision in my head is it's sort of like this ghostly, oh, now we're starting to remove electron density from between the two nuclei. And it diminishes the bond strength. So instead of having a triple bond, now we're down to a double bond. Now, importantly, we have unpaired electrons here. Molecular orbital theory predicts for O2 that you're going to have unpaired electrons. If you have unpaired electrons, we call that paramagnetic. A property of paramagnetic substances is they are attracted to a magnet. The opposite would be something that's called diamagnetic. With diamagnetic, they're all paired up. All the electrons in the molecule are paired up, and it's not attracted to a magnet. It's weakly repelled. When I mentioned earlier that we're going to add new properties tonight, these are the magnetic properties I was talking about. So I need you to know that something that is paramagnetic is attracted to a magnet, and that results when the molecule or atom includes unpaired electrons. The opposite is something we call diamagnetic. All the electrons are paired up, and it would not be attracted to a magnet. So let's now see how this applies if we look at other molecular orbital diagrams as we move across the second row. So I grabbed this one from the e-text. Here are the other diagrams that we have as we move across B2, C2, N2, O2, F2, neon 2. So I'm just moving left to right as I go across. They're not showing the ones that come from the 1s, but they're showing the groupings that I have beginning with the 2s and then the 2p's. And they've added in the correct number of electrons in each of the cases. So if I were to compare and contrast, it looks like there's a lot of similarities for what I have taken place on the left-hand side of the periodic table and the right. And by that, I mean, the electrons were added the same way in each of them. It sure looks like in each of the cases, they filled from the bottom up the correct number of electrons, and they put them in singly before they began pairing them up. It looks like that's what they did here. For O2, for each of the cases, I think electrons are always being added the same way. If we have the correct number of electrons, we just add them from the bottom up. We follow Hund's rule and the Pauli exclusion principle. So that's the same for all of them. It looks like the shape's also the same, because look at the designations. Sigma, sigma star, sigma, sigma star. The shapes are exactly the same in both of the cases. The only difference that I see is the relative energy seems like it flip-flops if I'm looking at this grouping. If I'm looking at things on the left-hand side of the periodic table versus that grouping on the right-hand side. That's the only difference. It turns out that the relative energy for these different molecular orbitals, it's pretty complex, okay? I'm trying to paint a simple picture for, oh, well, there's this one being found here, this one being found here. We can get the ordering for sure, but it's pretty complex. You've got a lot going on in terms of different number of protons, how the electrons are interacting with each other. It was complex when we were doing atomic orbitals too, and we had a shifting of the different energy levels. So it turns out this is the correct ordering for things on the left-hand side of the periodic table, and this is the correct ordering for things on the right-hand side. So one question people had in perusal is a good one is, well, what do we need to know about this? Well, I looked at the practice exam that we have. Here's the practice exam that were posted for midterm 3. This was the provided information right there. It says you'll be given a periodic table and the following supplemental information. And it had this image right here. So you're going to have exactly this image provided. It's showing you the grouping. This is what I believe it's showing. It's showing you the grouping for things that would be on the left-hand side of the periodic table and the things that would be on the right-hand side of the periodic table. So I can use and interpret these provided figures. Ask yourself, are you able to use these provided figures? Do you know what they're trying to represent? Let's practice that right here. So what type of MO do you think is being shown on those lines right there? What would be the designation for it? Think back, is that going to be bonding or anti-bonding? Is it going to be sigma or pi? Based on its placement right there, what do you think on that? I think that's going to be a pi that's anti-bonding that was formed from p orbitals overlapping with other p orbitals. I think this bottom group right here, this would have been sigma, sigma star. I've got two that are pi that would be bonding, sigma that would be bonding, pi star, and then sigma star. That's what I think goes with this. Here's another way that I've seen that same kind of question asked. How about this one? Here is a molecular orbital. Where would it be placed on this diagram? At positions 1, 2, 3, 4, 5, or 6? Where would this molecular orbital be placed relative to that picture right there? Position 1, 2, 3, 4, 5, or 6. I'm asking it this way because this sure sets up so it could be a multiple choice question, right? Both of these are ones that are really akin to how I see this questions asked on our exams. Take about 10 more seconds for me. Okay, let me share the results with you because I think they're really interesting. Okay, so as far as this one, the majority of folks, about 62%, are saying position 3 is the best choice. The other ones that were drawing folks voting were positions 4, and we had position 6 was getting a lot of initial votes. So as I look at positions 3, 4, and 6, I really like those being ones that you're considering. Because if I look at this molecular orbital, the first thing I'm going to do is I'm going to classify that as bonding because I do not see this vertical node. And I would also designate it as pi because I have electron density not along the internuclear axes, but above and below it. So if I'm seeking to answer this one, I'm designating this in my head first. It's saying, okay, this is a bonding arrangement. And it's also then going to be designated pi. The reason I like you all choosing 3, 4, and 6 initially, those are all spots where I would expect, where I know bonding molecular orbitals are found. So how do I decide amongst those? 6 would be sigma along the internuclear axis. 4 would be sigma along the internuclear axis. I think this goes with position 3 because I had 2 different arrangements for how I could have it pi. There were 2 degenerate molecular orbitals, above and below the internuclear axis and front to back. So the fact that folks were initially thinking of it in terms of bonding, outstanding. And the fact that the majority then put it at position 3, even better. This is a really high-end question. It's a typical exam question, but it's a high-end question. You're doing a great job thinking it through. Now, if I return back to this one, I've added some data here underneath, information about bond enthalpy, bond length, and whether it's paramagnetic or not, or diamagnetic. So for each of these, whether we're looking at the ones on the left-hand side of the periodic table or the right-hand side, I think we have enough information that we could calculate the bond order in each. In order to do that, notice how they've shown it. In red, I think they're trying to show, okay, there's no story here for bond order because you've got the same number in bonding and anti-bonding. So if you want to calculate the bond order, you could just look at the ones that are in green. I see 2 that are in bonding, 4, 6, 6, but then 2 that are in anti, and I start to diminish on that. So if I were putting in the bond order here, I think in B2, it's saying a single bond. In C2, a double bond. N2, okay, that's one we're familiar with. That would be a triple bond. O2 gets us back to a bond order of 2. F2, a bond order of 1, and no bond in neon 2. Notice how this connects great with the bond enthalpy. I go from a single bond to a double bond to a triple bond. The bond enthalpy goes up. 155, 495, 941. The bond is getting stronger. Look at the bond length. 1.43 angstroms, 1.21, 1.1. It's getting smaller. Look at this great relationship of how bond order matches up with bond enthalpy and bond length. So we've got great connections for how those are all fitting together. We want to know how bond enthalpy, bond length, bond strength, bond order all fit together. Now, as far as whether they have paired or unpaired electrons, I see B2 has 2 unpaired electrons. O2 has 2 unpaired electrons. Notice how that matches up then with it, whether it's paramagnetic or diamagnetic. The examples with unpaired electrons are paramagnetic. The other ones are listed as diamagnetic. Really typical application for this, something like this question. Which of these are going to be paramagnetic? For N2, they're all matched up. They're all paired up. For O2, I've got 2 unpaired. See if you can figure out for the ions right here. This is going to be one I'm going to send as a polling question to you. So take a second first. Which of these are going to be paramagnetic? Paramagnetic, recall, means that you have unpaired, at least one unpaired electron. Take your time on this one. When you're ready, take a stab at answering this poll, but no hurry. So in order to answer this one, in each case, we're looking at whether we have unpaired electrons or not. And we need to be careful when we're now looking at anions. Where do we place those next electrons? And does that lead to them being paramagnetic or diamagnetic? Take about 10 more seconds on that. Consensus on this one is that you have 2 examples that are going to be paramagnetic. The N2 2- anion and the O2. If I look within the set, I think that's an excellent call. I think if I have N2, initially they're all paired up. If I add 2 more electrons, they would go here unpaired. According to Hund's rule, I put in 1, put in the second. Okay, that would be N2. 2- would now be paramagnetic. O2 is paramagnetic. What if I add 2 more electrons to those? I'd add it to these 2 molecular orbitals, so it would turn it to be all paired up again. Really good job in terms of your analysis there. Now, this particular experiment, what does it look like? They're trying to show, this is a figure from the book, about what would happen if you add liquid oxygen and put it between the poles of a magnet. You know, I like teaching class somewhat from, I don't know, from my office right here, but I really miss the opportunity to do this experiment. This is one of the literally coolest experiments that we have. I got a demo for it, okay? So regretfully, I'm not doing this for you all right now, But let me show you what it looks like.
Talk about diamagnetism and paramagnetism. A diamagnetic substance has paired electrons in its molecular orbital diagram, while a paramagnetic substance has unpaired electrons in its molecular orbital diagram. We're going to look at this difference today with nitrogen and oxygen in their liquid forms. Nitrogen is diamagnetic. It has paired electrons in its molecular orbital diagram. We can see when we pour it on the magnet, the nitrogen passes right through. Oxygen, on the other hand, is paramagnetic. It has unpaired electrons in its molecular orbital diagram. You can see that the liquid oxygen sticks to the magnet until it boils away. This is due to the fact that the unpaired electrons in the molecular orbital diagram of oxygen make it literally magnetic.
Like I said, that one's pretty amazing. Now, this idea how O2 is paramagnetic, we saw that experimentally. I sort of want to wrap up our description of molecular orbital theory this way, because I said that, we have different bonding approaches. They allow us to predict different things. This simple Lewis structure does a good job of telling me, okay, you've got a double bond between the oxygen atoms. If I think about what would take place if I wanted to explain this with valence bond theory, I could explain a double bond by saying that you can have overlap between the p orbitals that are pointed at each other and overlap between ones that would be off of the axis. This is how valence bond theory I could use to describe a sigma bond and a double bond. With molecular orbital theory, this is my description that I have. Now, this one, as far as being paramagnetic, only molecular orbital theory tells me this. Molecular orbital theory tells me that I have two unpaired electrons. Where are the unpaired electrons in my Lewis structure? They're not to be found. Where are my unpaired electrons in valence bond theory? There aren't any. In valence bond theory, we've paired them up to form a sigma bond. We paired them up to form a pi bond. So if the question is, well, which of these is truly right? Molecular orbital theory is right. Okay, molecular orbital theory is the most complex that we've had out of the arrangement. But the fact that it describes and predicts the fact that O2 is paramagnetic, it tells me it's capturing an element of nature that the other ones, even though simpler, are not doing. So as I think about where we're at, where we're going, that's our end here of chapter 9. Within the learning objectives that I have listed, within chapter 9, we looked at the Vesper model. We connected it to polarity. We spent a little bit of time then looking at valence bond theory. We looked at that, how we would at times for hybrid orbitals, we could use that to form sigma and pi bonds. But the only thing within that segment that we haven't looked at was this topic of delocalized pi bonds. That's something we might pick up next class. I'll look to see how important that is for us, but we've done a lot with valence bond theory. And here's applications, suggested problems pertaining to molecular orbital theory. Notice it's introducing the property of magnetism and thinking about that. Which of particular ions would you expect to be paramagnetic? That's just filling in the molecular orbital diagrams. We also spent time interpreting the shapes. Remember back to this one, 3 different objectives. Can we populate and interpret the energy level diagram? Can we identify and understand the resulting shapes of the molecular orbitals? And third, can we connect the two? Can we show where those shapes are found on the energy level diagrams? Now, as we look ahead, last thoughts here to finish up, as we look ahead for your exam, these would be my suggestions. So I think it's really important to know the learning objectives for chapter 7, 8, and 9. Those are listed within the e-text and at the end of the chapter as well. It's really important to also then transform the instructional material. You've had information given to you in a lot of different ways. I would try to take the information for chapter 7, chapter 8, chapter 9, in each of those cases, summarize it in a way that makes sense for you on like one page of paper for each one. I've been trying to give you information with these overviews for chapter 7, chapter 8, start of chapter 9. Those are the key essential ideas that I know should be on your instructional material that you transform. Summarizing, how do you answer questions about effective nuclear charge? How do you summarize and answer questions about lattice energy? The idea of being able to authentically test yourself, that's what I was trying to provide with those previous overviews as well. But I know that we have within that a great set of practice exams. I see 3 different practice exams that are listed within Carmen. All of these are going to be great resources for you to address weaknesses, look at supporting videos, ask me for help if you get stuck along the way. We're in a really unique position because when I looked at when the exam is within this one, all of our other exams in this class are on Mondays. This is the only one that falls on a Wednesday. Or if you have an in-person lab that you're participating in, it would be on the Thursday. The reason I point this out is this is our best chance to be able to cover ideas on the day before the test and have it help you. I really want to help you in class next Tuesday. The only way I can do that, you got to give me data. You've got to show me what you can do in the practice tests. I want to make that time specific to help you. Okay, you're here tonight. You're going to be here next Tuesday. Please give me data. Work within the practice tests. Let me see what you can do. Use the supporting videos and suggested problems there. Get better. Because if we can spend time next Tuesday and I address the key things that you're still struggling with, that will absolutely be great. If I'm struggling to get information about what you can or can't do, I'm just going to be guessing and it's not going to be as effective. Okay, so this whole idea of addressing your weaknesses, please do your best to let me know what those are so then we can really do great in class next Tuesday and dominate the subsequent test. Okay, folks, I'll be hanging around if you got questions. Enjoy the great weather, and as always, I appreciate your attention.
For an H2O molecule, it's going to have sp3 orbitals, right?
Tell me what kind we're looking at.
An H2O molecule is sp3 orbitals?
Correct. Yep.
And that's, are there going to be 4 of those, or is there only going to be 2?
For an H2O molecule, I'd say my central atom right there is sp3 hybridized. Mm-hmm. I'm looking at saying, okay, I've got a tetrahedral electron domain. So I'm going to say the hybridization must be sp3. So I'm going to have a total of 4 sp3 hybrid orbitals. One will contribute to a sigma bond, one will contribute to a sigma bond, one will be holding a lone pair, and the last one will be holding a lone pair.
Okay, so anytime you have sp3 hybridized orbitals, is there always going to be 4 of them on any individual atom?
Yep, you got it.
Okay, thank you.
Dr. Clark, could you explain again why the second row elements have different molecular orbital diagrams?
Yeah, so the picture that we have when we're initially looking at the energy for them is to say, all right, let's just take the one on the left and the one on the right and consider those orbitals, those atomic orbitals independently, and let's see how they overlap. Okay, great. You've got a p orbital on the left-hand side and a p orbital on the right-hand side, and they're pointed right at each other. Let's look to see the resulting molecular orbital shape that we get. That's our simplest approach, but that doesn't really capture entirely what's going on, because it's a bit of an overstatement to say, hey, a p orbital and another p orbital, hey, forget about all the other ones that are there. Forget about all the other atomic orbitals that are there. Just like pick all of those away and just look at the ones that you're interested in. Turns out you can't really do that all the time. So that's what we find as we are looking at the left-hand side of the periodic table and the right-hand side. What's changing is the relative size of those as we move left to right. So the manner in which they interact, our ability to say, hey, ignore all the other ones or not, that's what changes a little bit along the way. I come back to the idea that when we're thinking about atomic orbitals or molecular orbitals, we can't think of them as just being fixed and they're always exactly the same energy and exactly the same everything. They're not. They change as we begin to populate other ones as well. We saw that the 3D electrons, for example, for the atomic orbitals, those shifted as we added more and more electrons along the way. It's like a moving target a little bit with us. And that's the same thing that's taking place with our molecular orbitals. Now, fortunately, within here, we don't have to really dig too deep into that. And in fact, the only two different sets that we're looking at are shown right here. A grouping for what works on the left-hand side of the periodic table and a grouping for what works on the right-hand side. This labeling above where it's saying this 2s 2p interaction, that's what it means as far as, does the atomic orbital interact with other ones as well, or could we look at it independently? But in a way, we don't really need to worry about where that part comes from. Some textbooks just say, you know, it's complex. Let's just take it with what it actually is, and that's fine.
Okay, I sort of get it. It's because as you move farther right, there are more electrons occupying the space, I guess, and that changes how the molecular orbital is.
Yeah, well, in a way, when we were looking at the ones for atomic orbitals, and we were looking at how, okay, initially the 2s and 2p were on the same energy level for hydrogen. And then once we added more electrons, we saw how the 2s and the 2p split out from each other. In a way, what we did then is say, you know, there's a lot of interactions going on. This gets complex. Let's just take and use the ones that are actually there. And that's the same thing we're doing here. We're using the ones that experimentally are actually there.
Thank you.